If you could travel at the speed of light, 300,000 km per second, it would take 93 billion years to cross the observable universe. But what's the catch? The universe is expanding faster than you can move. You'll never reach the edge. Never. You'll race forever, and the horizon will run away from you further and further, until the very fabric of space stretches so much that the stars will go out one after another. The galaxies will disappear from sight, and you will be left completely alone in the endless cold, a completely black void. This is not science fiction. This is the reality in which we exist right now. Today, we're going to go on a journey that will change the way you perceive your own existence. We'll start from the surface of the Earth, from where you are at this very moment, and we'll move away. Slowly at first, then faster and faster. We will pass through the atmosphere, pass the moon, leave the sun behind, and leave the solar system. We will go beyond our stellar arm, leave the Milky Way galaxy, rush through the cluster and a supercluster of galaxies, and finally, we reach the very edge of the observable universe, the limit beyond which light hasn't had time to reach us yet since the Big Bang. But this is only the beginning, because beyond this edge, there exists something even more frightening. Something that science prefers to speak about in whispers. Something that makes the most eminent physicists of our time doubt the nature of reality as such. 3 mysteries will haunt us throughout this journey. The first is the paradox of scale. Why does the universe so large that the human mind is physically incapable of comprehending its true dimensions? Our brain evolved to survive in the African savanna and to estimate the distance to predators and prey. The most he can intuitively understand is a few kilometers, and we have to operate with numbers with so many zeros that just pronouncing them takes minutes. The second riddle, the paradox of emptiness. The universe almost completely empty. If you could randomly pick a point in the universe and teleport there with a 99.99% probability, you would find yourself in a complete vacuum in millions of light years from the nearest star, in complete darkness and silence. Matter, planets, stars, galaxies, these are the exception. An anomaly. Tiny islands of matter in the ocean are nothing. The third mystery is the most disturbing. The paradox horizon. What we call the universe is just a tiny bubble, limited by the speed of light and age. Space. Beyond this bubble, there is an infinity that we will never see, never explore, will never know. There could be other forms of matter, other laws of physics, other dimensions, or there could be absolute nothing. We will never know. This knowledge is forever hidden from us, from the structure of reality. Today, you will learn something that will change the way you look at the night sky, something that will make you feel anew your place in this endless drama. And maybe, just maybe, knowledge will keep you awake, or, on the contrary, will bring a strange paradoxical peace. I'm fascinated by the mysteries of space. If you want to touch the boundaries of human knowledge, subscribe to channel. The journey begins right now. Let's start with what seems obvious, with what we were taught in school. From the picture of the universe that exists in most people's heads, Earth is the third planet from the Sun. The diameter is about 12,700 kilometers. We revolve around an ordinary yellow stars at a distance of approximately 150 million kilometers. Our solar system is one of many in the Milky Way galaxy, which contains approximately 400 billion stars. The Milky Way path is one of approximately 2 trillion galaxies in the observable universe. All it is located in the space that appeared 13.8 billion years ago as a result of the Big Bang explosion. Sounds impressive, right? Billions of stars, trillions of galaxies, huge numbers. But here's the problem. This picture is a radical simplification. It looks like you're trying to explain the structure of the ocean by showing someone a glass of water. Technically correct. It's almost a complete lie because we're not just underestimating the size universe, we underestimate them catastrophically, on the order of such the number of orders of magnitude that these orders themselves become meaningless numbers. Let me show you how this is where the deception lies. When we are told that the Earth is 150 million kilometers from the Sun, that sounds like a big number. 150 million is impressive. But the human brain is not capable of truly imagining this distance. We just hear a lot, and we nod our heads. Let's try it differently. If you got in the car and drove to the Sun at a speed of 100 km/h, without stopping for a second or sleep, no food, no gas, it would take you 171 years, almost 2 centuries of continuous travel. You would have started the journey young and arrived never, because you would have died long before your goal. Your children would have died, your grandchildren would have died, and only your great-great-grandchildren, if they continued the journey, would be able to see the Sun up close. This, the distance to the nearest star to us, to our own star. And now imagine Neptune, the most distant full-fledged planet in the solar system. It is 30 times farther from the Sun than Earth. That's 4.5 billion kilometers. By car, 5,000 years. 5,000 years. Continuous movement. When you started this journey, the Egyptian pyramids were not built. Writing was just emerging. Humanity did not yet know what is a wheel. And this is still our solar system, our home, tiny corner of space that we are accustomed to consider our own. But the solar system is not ends at Neptune. Beyond it lies the Kuiper Belt, a vast region of icy bodies home to dwarf planets like Pluto and Eris. And beyond the Kuiper Belt lies the aortic cloud, a giant spherical shell of comets and icy debris that surrounds the Sun at a distance of up to 100,000 astronomical units. An astronomical unit is the distance from Earth to the Sun. 100,000 such distances. If you remember that it's a car ride to the Sun, 171 years, then the aorta cloud's outer edge is 17 million years away. And this is where it begins the first break in consciousness, because all this is Earth, Mars, Jupiter, Saturn, Neptune, Pluto. The entire aorta cloud is not even a speck of sand. It's not even an atom in a speck of sand. This is something immeasurably smaller when compared to the scale of a galaxy. The closest star to the Sun is called Proxima Taurus. It is located at a distance of 4.24 light-year. A light-year is the distance that light travels in 1 Earth year, moving at the speed 300,000 kilometers per second. That's about 9.5 trillion kilometers. Let's translate that into something more understandable. Language. By car to Proxima Centauri, 47 million years. When would you start? Is this a journey? The ancestors of modern apes still roamed the Earth. Humans weren't even a concept yet. Dinosaurs became extinct just 18 million years ago. The continents looked completely different. And it is the nearest star, the closest of all the stars in the universe. Now, the fun begins. At school, we're shown pictures of the Milky Way galaxy, a beautiful spiral of stars. And we think, well, yes, there are a lot of stars there, tightly packed together. But that's also a lie. A galaxy is not a dense cluster. A galaxy is almost complete, a void with rare inclusions of matter. The average distance between stars in our region of the Milky Way is about 4 to 5 light years. But stars are tiny dots compared to these distances. If the sun were the size of an orange with a diameter of 10 centimeters, then the nearest star, the same orange, would be located at a distance of 3,000 kilometers. Imagine, one orange in Moscow, another in Novosibirsk, and nothing between them. An absolute vacuum. That's what it is. A galaxy, in fact. Not a cluster of stars, but an endless void with a vanishing rare spangles of light. And here, school education begins not just to simplify, it begins to actively introduce misconception. When we are told that there are 200–400 billion stars in the Milky Way, we imagine something grandiose, but we don't understand how rarefied this grandeur is. The diameter of the Milky Way approximately 100,000 light-years. That's a quintillion kilometers, a number with 18 zeros. If you could move at the speed of a car, it would take you 1 trillion years to cross our galaxy. Trillion years. The universe is only 13.8 billion years. It would take you 70 times longer than it took for the universe to exist. Reality. And this is just one galaxy. Our galaxy is home. But we said that there are 2 trillion galaxies in the observable universe. 2 trillion. 2 from the bottom. Zeros. If you started counting galaxies at 1 per second, you wouldn't stopping. It would take you 63,000 years. 63,000 years of continuous counting, and you would have just finished listing the galaxies. But here's what really knocks you off your feet. When we talk about 2 trillion galaxies, we're only talking about the observable universe. That's just the part of space that's light from which managed to reach us in 13.8 billion years. This sphere with a radius of approximately 40 billion light-years. Yes, more than 13.8, because the universe was expanding while the light was traveling toward us. Beyond this sphere, there is a universe that we do not see, and will never see how large this invisible part is. Astronomers are trying to estimate. Some models suggest that the full universe could be 10 to the power of 23 times larger. Observable. It's a 1 followed by 10 zeros. If the observable universe is atom, then the entire universe could be the size of several galaxies. Other models suggest that the universe infinite, literally not very big, not unimaginably huge, but mathematically endless, without edge, without border, stretching forever in all directions. And here the official picture that was painted for us at school is finally crumbling because we were told about the Big Bang as an explosion at some point that created space expanding into some external nothingness. It's a convenient metaphor, but it's wrong. The Big Bang happened everywhere at once, not in one spot, expanding outward, and at every point of infinite space simultaneously. If the universe is infinite now, it was infinite at the moment of the Big Bang, only infinitely hot and infinitely dense. Your mind resists this idea. That's normal. The human brain did not evolve to understand infinity, but reality does not have to conform to our intuitions. And now, when we have destroyed the cozy school picture of the world, when we have seen the true chasm between what we were told and what actually exists, we can begin the real journey. But reality is much stranger than mere numbers and distances, because behind the dry numbers lies something that turns all our ideas about humanity's place in the universe upside down. Statistics hide phenomena so alien to our everyday experience that language itself becomes insufficient for them descriptions. We're used to thinking of space as an empty container in which objects are located. Stars here, planets there, galaxies everywhere. The emptiness between them is just the absence of something. But modern physics tells us that space it's not a container. Space is an entity. It can bend, stretch, vibrate. It can be born and possibly die. Space is the same physical an object like a star or a planet is just a completely different kind. And that space expands, not in the sense that galaxies are flying apart through some external void, but in the sense that the space between galaxies itself is expanding. New space appears everywhere every second. Distant galaxies don't fly away from us through space. They are stationary relative to their local space, but this space itself is stretching, expanding, and the galaxies are carried away along with it. And here comes a truly eerie fact. Galaxies that are quite far from us, they move away faster than the speed of light. Not because they move so fast. Nothing can move faster than light through space. But space itself is not required to obey this limitation. Space can expand at any speed, and it does. Galaxies beyond the so-called event horizon. The universe is forever lost to us. The light they emit now will never reach Earth. Never. Even if the universe existed forever, these galaxies are already carried beyond the reach of the universe. Every second, more galaxies cross this horizon. Every second, the universe becomes a little lonelier for us. Space is shrinking not physically, but in terms of what we will ever be able to see, study, and achieve. In the distant future, trillions of years from now, all galaxies outside our local cluster will disappear horizon. If by that time there are intelligent beings in the Milky Way, they will look at the sky and not see nothing but their own galaxy. They will not know about the existence of other galaxies, will not be able to find out. All modern cosmology will become impossible. They will live in a universe that will seem to them small and understandable, and they will make mistakes. Just as we were wrong looking at school pictures of galaxies. But that will happen in trillions of years. Now we are surrounded by something completely different. Now we find ourselves at a unique moment in cosmic history, a moment when the universe is young enough to show us its secrets, but it is already old enough for these secrets to be quite dramatic. We can see cosmic microwave background radiation, light left over from when the universe was only 380,000 years old. We can see galaxies that formed when the cosmos was less than 1 billion years old. We can look back billions of years, and see what the world was like before the Earth appeared, before the Sun appeared, before the emergence of our galaxy. And all this is thanks to one strange property of light. Light has a finite speed. When you look at the moon, you see it as it was just over a second ago. When you look at the sun, you see its 8-minute version. When you look at Proxima Centauri, you see the star as it was 4 years ago. And when astronomers look at distant galaxies, they see light that has traveled billions years. They see the past. They look at history. And this history tells us something strange. The universe wasn't always like it is now. It's evolving, changes, becomes different with every billion years. In the early universe, galaxies were smaller, brighter, more active. Stars were being born at a frantic pace. Black holes were devouring matter with a greed that the modern universe has already lost. The cosmos was more chaotic, energetic, and dangerous. Now the universe is aging. Stars are being born less and less often. Galaxies are becoming quieter. Matter is slowly accumulating into black holes and cooling stellar remnants. The cosmos becomes quieter and darker, and one day it will become completely dark. But we'll talk about that later. Right now, we need to understand one more thing. Everything we discussed before so far, galaxies, stars, distances, are only a small part of what exists in the universe. Literally small, about 5%. Ordinary matter, atoms, of which everything we can see and touch consists of, it makes up about 5% of the total energy and matter of the universe. 5%. Another 27% is dark matter. We know it exists because we can see it. Gravitational influence. Galaxies rotate too fast to hold together without additional invisible mass. Dark matter is all around us, passing through us every second, but we don't know what it is. And the remaining 68% is dark energy, a mysterious force, which causes the universe to expand faster and faster. We don't know what it's like this. We don't understand where it comes from. We don't know how it works. 95% of the universe is something we know almost nothing about. And now you begin to understand how deep is the abyss that we call human ignorance. We are proud with our telescopes and particle accelerators. We send probes to distant planets and map billions galaxies. And yet we have no idea about the nature of 95% of them, of all that exists. The reality is much stranger and much darker than any picture we were shown. Now that we've shattered the illusion understanding, let's start building a new picture, more honest, more frightening, but also more beautiful in its unimaginable complexity. To do this, we need to understand how scientists measure things in general, these monstrous distances, because you can't just stretch a tape measure to the nearest galaxy. You can't send an umbrella into the air and measure how long it takes to fly. The distances involved are too great for any direct measurement. Instead, astronomers use what's called the cosmic distance ladder. It's a sequence method where each subsequent step builds on the previous one, allowing us to reach further and further into space. The first step of this ladder is parallax, a method you can test directly now. Stretch out your arm and raise your finger in front of your face. Now close your left eye and look at your finger. Then close your right eye and look again. The finger has shifted relative to the background. Correct. This is parallax, the apparent displacement of an object when changing observation points. Astronomers do the same thing, only instead of their eyes, they use the position of the Earth at different times of the year. In January, the Earth is on one side of the Sun, in July on the opposite side. The distance between these two positions is about 300 million kilometers. This is the base of our giant triangle. Observing nearby stars from these two positions, astronomers notice a tiny displacement relative to more distant stars. By measuring this angle with incredible accuracy, one can calculate the distance to stars. 8th grade geometry, only the scale is completely different. But here's the problem. Parallax only works for relatively nearby stars. Even with the most precise modern instruments, such as the spacecraft with the Gaius telescope, which measures the position of stars with an accuracy of millionths of an arc-second, we can reliably measure the distance by parallax only up to a few thousand light-years, several thousands of light-years, and the diameter of our galaxy is 100,000 light-years, and to the nearest large galaxies are millions of light-years away, and distant galaxies are billions. Parallax is just the first step of a very long ladder. The next step is standard candles, objects whose absolute brightness we know or can calculate. If you know how bright the light source actually is, and you see how dim it appears from the ground, tells you how far away it is. Light dims as the square of the light. Distance. Double the distance, and the brightness will drop by a factor of 4. One of the most important standard candles, Seifts. These are pulsating giant stars, the brightness of which changes with a very regular period. At the beginning of the 20th century, the American astronomer Henrietta Leavitt made an amazing discovery. The pulsation period of Cepheid is directly related to its absolute brightness. The longer the period, the brighter it is. star. This discovery changed astronomy forever. Now it was possible to find a Cepheid star in a distant galaxy and measure it. The period of its pulsation, calculate its true brightness, and, comparing it with the observed brightness, determine distance to the galaxy. This is how Edwin Hubble proved in 1924 that the Andromeda Nebula is not part of the Milky Way, but a separate galaxy. He found Cephei in Andromeda and calculated that it is located approximately 900,000 light-years away, far beyond our galaxies. This distance was later refined to approximately 2,000,000 light-years. But the principle itself remained unchanged. The Cepheids became beacons illuminating the road to deep space. But Cepheids also have their limits. Even the brightest of, they are visible only to distances of several tens of millions of light-years. For more distant galaxies, brighter candles. And this is where Ia-type supernovae come into play. When the white dwarf, the remnant of a star like our Sun, accumulates enough mass from its companion star that it reaches critical limit of 1.4 solar masses. At this point, thermonuclear explosion occurs, an explosion of colossal power. The white dwarf is completely destroyed, ejecting matter into space at a speed of tens of thousands of kilometers per second. The beauty of this process is in its standardization. Since the explosion occurs at a strictly defined mass, all new types of Io have approximately the same absolute brightness. At their maximum, they shine brighter than 5 billion suns. Such flares are visible at distances of billions of light-years. It was the supernovae of the Ia types that allowed in 1998, one of the most stunning discoveries in the history of cosmology was made. The expansion of the universe is accelerating. Distant supernovae turned out to be dimmer than expected. Galaxies, in the regions where they exploded, were located further away than predicted by the model of a uniformly expanding universe. Something was pushing the cosmos from within. Something was forcing the galaxy to run away faster and faster. This something got the name of dark energy. And for this discovery, the Nobel Prize in Physics was awarded in 2011. But let's get back to scale, because even with parallax, Cepheids and supernovae, we measure only islands of matter, individual stars and galaxies. We need to understand the structure of the void between them. Here's the fact, which is rarely mentioned in popular descriptions of space. When we talk about the quality of distances between galaxies, we're talking about distances between centers. But galaxies aren't points. They're extended objects with blurred boundaries. Let's take our nearest large neighbor, the Andromeda Galaxy. Its center is located approximately 2.5 million light-years from the center of the Milky Way. But Andromeda's diameter is about 220,000 light-years, and the diameter of the Milky Way about 100,000. If we take into account the fuzzy halos of dark matter surrounding both galaxies, it turns out that they are almost touching. And indeed, the Milky Way and Andromeda are approaching each other. In 4 to 5 billion years, they will collide and begin to merge into one giant galaxy. But we'll talk about that later. Right now, it's important to understand something else. Galaxies are not evenly distributed throughout the universe. They gather in groups and clusters. Clusters are grouped together in supercluster, and superclusters line up into giant structures, filaments and walls separated by huge voids. Our galaxy is part of the so-called local group, a cluster of approximately 80 galaxies, stretching over 10 million light-years. This group is dominated by two spiral galaxies, the Milky Way and Andromeda. The rest are mostly dwarf galaxies, many of which are satellites of these two giants. Local. The group, in turn, is located on the outskirts of the Virgo cluster, a giant collection of more than 2,000 galaxies, the center which is located approximately 54 million light-years from us. At the center of the cluster, Virgo, lies the giant elliptical galaxy M87, a monster containing several trillion stars and a supermassive black hole with a mass of 6.5 billion suns. It was this black hole that became the first to obtain an image of that famous orange donut, published in 2019. But the Virgo cluster is only part of the larger structure. It is part of the Virgo supercluster, which itself is part of an even larger formation of Laniakea. Laniakea comes from the Hawaiian word for unbounded heavens, is a supercluster of superclusters, a giant gravitational pool into which hundreds of thousands of galaxies flow, diameter of approximately 520 milliards light-years. This is so much that the light emitted from one edge of Laniakea will reach the opposite edge in 520 million years. When this light was released, complex life did not yet exist on Earth. The first multicellular organisms were only appeared, and here is where the scale really begins to weigh on the mind. Laniakea contains approximately 100,000 large galaxies and even more dwarf ones. The total mass is about 10 in solar masses, 100 quadrillion solar masses, a number with 17 zeros. But Laniakea is just one supercluster among many. Nearby are other giant structures: the Perseus Pisces supercluster, the Indian Peacock supercluster. The Shapley supercluster is one of the most massive known structures in the universe. These superclusters are connected between themselves even more grandiose formations, galactic fibers or filaments. Imagine a sponge. The solid material of the sponge is made up of fibers containing galaxies. The voids inside sponges are cosmic voids, gigantic areas of space, almost devoid of galaxies. The largest known structures in the universe are precisely such filaments. The Great Wall Sloan extends for 1.3 billion light-years. The Great Wall of Hercules from the North Corona at 10 billion light-years, although its existence as a single structure is disputed by some astronomers. And here, we encounter a fundamental problem. According to the cosmological principle, one of the basic postulates of modern cosmology, the universe should look the same on average at any point and in any direction. On sufficiently large scales, inhomogeneities should smooth out, and space should become smooth and homogeneous. But when we find structures the size of billions of light-years, we begin to doubt whether such a scale on which the universe exists at all becomes homogeneous, or heterogeneities continue at all scales up to the boundaries of the observed universe. It's an open question. We don't know the answer, but let's continue. Increase the scale. The observable universe is shaped like a sphere with its center at the point of observation, that is, where there is an observer. For us, this is the Earth. The radius of this sphere is approximately 46 billion light-years. This may seem strange. If the universe is 13.8 billion years, why is the radius of the observable universe larger? The answer lies in the expansion of space. The light that we see now from the most distant galaxies was released when these galaxies were much closer to us. But while the light was flying towards us, space expanded, and the galaxy was carried away. It is now 46 billion light-years away. Although the light from it traveled for only 13 billion years, the diameter of the observable universe is approximately 93 billion light-years. That's 880 sextillion kilometers, a number with a difference of signs. If you could travel at the speed of light, you would need 93 billion years to cross the observable universe. But the universe is expanding, so you would never complete the journey. The goal would run away from you faster than you would approach it. The observable universe contains approximately 2 trillion galaxies. But this number is only an estimate based on extrapolation from observations. We can directly observe only a tiny fraction of these galaxies. Most of them are too dim, too distant, or hidden from us by the dust and gas of the Milky Way. The total number. The number of stars in the observable universe is estimated at 200 sextillion. Millions, millions, millions. That's about 10 times more than the number of sand dunes on all the beaches on Earth. Total. We don't know the exact number of planets, but if on average there is at least one planet per star, then there are about as many planets as there are stars, or more. Hundreds of sextillions. Planets. And each of them has its own geology, its own history, perhaps its own life. But here's what's really confusing. All this, all the galaxies, all the stars, all the planets, all the black holes, all the dust and all the gas make up only about 5% of the total energy mass of the universe. The remaining 95% of dark matter and dark energy are distributed completely differently. Dark matter is concentrated in halos around galaxies and galaxy clusters. Dark energy appears to be distributed uniformly throughout space. And when we talk about the scale of the universe, we must remember that visible matter is only the foam on the surface of the invisible ocean. Imagine that you are studying the ocean, but you only see air bubbles on its surface. You can map these bubbles, measure their sizes, track their movements, but you know nothing about deep currents, about pressure at the bottom, about life in the abyss. Bubbles are the result of processes you can't directly observe. This is precisely the state of modern astronomy. We see only bubbles, luminous matter. The ocean remains invisible, but even studying these bubbles brings amazing discoveries. One of the strangest properties of the universe on large scales is characterized by its homogeneity and isotropy. Wherever we go, if you haven't looked, space looks roughly the same. The distribution of galaxies on very large scales is uniform. The cosmic microwave background radiation is the same in all directions with an accuracy of up to 100,000ths. Shares. It seems natural, but in fact, it is a deep mystery. The point is, the fact that different parts of the universe were never in contact with each other. Light from one part would not have time to reach another in the entire existence of space. They never exchanged energy, information, or anything. They were and remain completely isolated from each other. And yet, they look the same, have the same temperature, contain the same proportions of elements, and obey the same physical laws. How is this possible? Standard. The answer of modern cosmology is inflation. The hypothesis is that in the first moments after the Big Bang, the universe went through a period of ultra-fast exponential expansion. In a split second, it increased in size by an unimaginable amount, perhaps 10 to the power of 26 times or even more. Before inflation, the universe we observe today was a tiny region smaller than an atom. This region was homogeneous because it was small enough to establish equilibrium. Then inflation stretched it to colossal proportions, preserving homogeneity. It's an elegant explanation, but it raises new questions. What triggered inflation? Why did it stop? What happened before it? And the main question, if inflation, what really happened is beyond the region it stretched. Some models suggest that inflation continues forever in other regions beyond our observation. These regions form other universes, perhaps with other physical constants, other laws, other properties. The collection of all such universes is called the multiverse. If this hypothesis is correct, then the observable universe is just one bubble in an infinite foam, one of the infinite set. Not unique, not special, just one of. But we can't verify this hypothesis. By definition, other universes, if they exist, are cut off from us. No signal can penetrate from one bubble to another. This is the boundary of knowledge, a wall that perhaps impossible to overcome. But let's get back to what we can observe. The observable universe is not the whole, the universe. This is only that part of it from which light managed to reach us. Beyond the observable universe, space continues, perhaps forever. Modern observations impose limitations on the size of the complete universe. If the universe were closed, finite, but boundless, as if we were to observe the surface of a sphere, we might see traces of this closure in the cosmic microwave background radiation data. We don't see them. This means that either the universe is infinite, or it is so much larger than the observable region that we cannot notice its curvature. The minimum size of the complete universe, according to observations, is approximately 400 times larger than the observed one. This means that if the observable universe is a sphere with a diameter of 93 billion light-years, then the complete universe could be a sphere with a diameter of at least 37 trillion light-years. But this is the minimum. The actual size may be immeasurably larger or infinite. And here science honestly admits its impotence. We don't know what is the true shape of the universe. We don't know whether it is finite or infinite. We know what lies beyond the observable horizon. We don't know whether our universe is one or infinite. Many. These questions may never be answered, not because we're not smart enough or our tools aren't not powerful enough, but because the very structure of reality may forbid us get these answers. The horizon of the observable universe is not a technological barrier. It is a physical one. The limit. Light that hasn't reached us will never convey information about what lies beyond it. That's not a question. Time. It's a matter of principle. We are locked inside a light cone. Everything that is beyond its limits, inaccessible forever. This knowledge is simultaneously humbling and liberating. Humbling because it reveals the limits of human knowledge. Liberating because it reminds me there are mysteries that don't need to be solved. They can simply be accepted. But inside the light cone, within the observable universe, there is still so much unknown. Every year, astronomers are discovering new phenomena that don't fit into existing models. New types of objects, new data anomalies, new mysteries. One of the most intriguing is the cold spot, a region of the cosmic microwave background radiation in the constellation Eridanus that is slightly cooler than it should be statistically. The diameter of this region is about 5 degrees on the sky, which corresponds to about 1 billion light-years in real space. What it is, we don't know. Perhaps it's just a statistical fluctuation, a random occurrence that doesn't mean anything. Perhaps it's the trace of a giant void, a region of space almost devoid of matter. Perhaps, and this is the most exotic hypothesis, it is a trace collisions of our universe with another universe in the early stages of cosmic history. We cannot prove any of them. These hypotheses, we can only continue to observe, collect data, build models, and accept that the final, we have no answers. This is the honest state of modern cosmology. We know an incredible amount about the universe. We've built models that explain the evolution of the cosmos from the first microseconds. After the Big Bang to the present day, we predicted the existence of a relic radiation, the distribution of light elements, the large-scale structure of the universe, and all these predictions confirmed. But the more we learn, the more clearly we see the limits of our knowledge. Dark matter, dark energy, inflation, the nature of space and time. origin, physical laws. The universe remains a mystery, a beautiful, frightening, endless mystery. And maybe that's the best thing that can be said about it. Now let's fill this abstract picture with concrete examples, because numbers in themselves, they are just symbols on paper. To truly feel the scale of the universe, you need to see individual objects, compare them with each other, feel how your idea, the great, crumbles to dust when confronted with cosmic reality. Let's start with what is very close, with our own sun. The sun seems enormous to us. From Earth, it occupies about half a degree sky, enough to fill the world with light and warmth. Its diameter is about 400,000 kilometers. This is 109 times the diameter of the Earth. If the sun were hollow, about 1 liter of 300,000 planets the size of Earth would fit inside it. It sounds grandiose, but the sun it's a dwarf. No, literally. In astronomical classification, the sun is classified as a yellow dwarf, a star main sequence of spectral class G. These are the most common and most ordinary stars in the universe. Nothing special. The middle of the statistical distribution. Let's climb the ladder of stellar sizes. Arcturus, the brightest star in the constellation Bootes, the fourth brightest star in the night sky. In the sky. It is an orange giant, the diameter of which is approximately 25 times larger solar. If Arcturus were in the position of the sun, it would fill a significant portion of Mercury's orbit. But Arcturus is just a giant, not a supergiant. Galaxies is red, a supergiant in the constellation Orion, one of the most famous stars in the sky, marking the shoulder of the mythological hunter. Its diameter is estimated to be approximately 700–800 times that of the sun. If Betelgeuse occupied the place of the sun, its surface would extend beyond the orbit of Mars, possibly beyond the orbit of Jupiter, would be located deep inside the star in the hot layers of plasma, and Belgium is unstable. It pulsates, changing its size and brightness. Astronomers expect that in the next 100,000 years, perhaps much earlier, it will explode as a supernova. The flash will be visible to the naked eye even during the day. In a few weeks, Betelgeuse will be the brightest object in the night sky after the moon. But Betelgeuse is not the biggest a famous star. This title belongs to objects so colossal that the human mind refuses to comprehend them. Perceive. Stevenson, 218. Red supergiant in the constellation Scutum on approximately 20,000 light-years from Earth. Its diameter is estimated to be approximately 2,150 times larger than the Sun's. If it were in the Sun's place, its surface would extend beyond the orbit Saturn. Try to imagine it. A star so huge that inside, it would fit the orbits of Mercury, Venus, Earth, Mars, Jupiter, and Saturn. All these planets with all their geology, all their satellites, with their entire history, would be located deep inside one glowing ball of hot gas. It takes light approximately 8.5 hours to cross Stephenson's diameter 218, 8.5 hours at 300,000 km/s. And even that's not the limit. There are objects that are even more extended, although not necessarily more massive. Some planetary nebulae, shells of gas ejected by dying stars, stretch for light years. Supernova remnants expand over millennia, covering areas of space comparable to the distance to the nearest stars. The Crab Nebula. A supernova remnant observed by the Chinese astronomers in 1054 has a diameter of approximately 11 light-years, and it continues to expand at a rate of about 1 liter per second. But let's go even higher on the size scale. Galaxies. Our Milky Way, a spiral galaxy with a diameter of about 100,000 light-years. It seems huge compared to the stars. But among galaxies, the Milky Way is average. Not small, but not giant either. The Andromeda Galaxy is our closest large neighbor, about twice its size. The diameter is estimated at 220,000 light-years. It contains approximately 1 trillion stars, several times more than the Milky Way. But there are galaxies, compared to which even Andromeda seems modest. IC101 is a giant elliptical galaxy in observable 2022 cluster, at a distance of approximately 1 billion light-years, years from Earth. Its diameter is about 4 million light-years. This is 40 times larger Milky Way. It contains approximately 100 trillion stars. 100 trillions is a number that is impossible to comprehend. If you were to count the stars in this galaxy at 1 per second, it would take you 3 million years. And even 1101, it's not the largest known galaxy. Several candidates contest that title, including Alcyonius, a radio galaxy with giant jets extending 16.5 million light-years. 16.5 million light-years. The distance that light travels in 16.5 million years. A single object stretching that distance. When the light left one end of Alcyonius, the dinosaurs became extinct on Earth. When he reaches the other end, humanity, if it still exists, will have changed to unrecognizable. But even galaxies aren't the largest structures in the universe. Galaxy clusters combine hundreds and thousands of galaxies into gravitationally bound systems. The Coma cluster, one of the nearest large clusters, contains over 1,000 large galaxies and extends for 20 million light-years. The Perseus cluster, in the Fornax cluster, into the Centaurus cluster. Each of them is a gigantic collection of stellar islands, floating in a sea of dark matter. A supercluster, a collection of even larger clusters. The Shapley supercluster, one of the most massive known formations, contains more than 8,000 galaxies and extends for approximately 650 million light-years. And finally, galactic filaments are the largest known structures in the universe. Threads of matter connecting clusters of galaxies into a cosmic web. Filament Hercules, the Northern Crown, if its existence is confirmed as a single structure, extends for approximately 10 billion light-years. This is approximately 1/7 of the diameter of the observable universe. One object, 1/7 of the entire visible space. But here's what's special. It's strange. These giant structures, fibers, and walls are not dense formations. They are rarefied almost as much as the voids between them. The difference is density by only a few times. The entire large-scale structure of the universe. It's a slight ripple on an almost perfectly smooth surface. The irregularities that look grandiose up close, almost disappearing on the largest scales. Space strives for homogeneity. Any disturbances are smoothed out, dissolved, lost in the infinite space. And now that we've seen the scale of space, it's time to see the scale of energy. Because the universe is not a museum of static exhibits, it is an arena of continuous violence, a place where processes of such destructive force occur that human language stalls when trying to express them. Describe. Let's start with what seems peaceful, with our sun. Every second, the sun converts approximately 600 million tons of hydrogen into helium. Of this, about 4 million tons of mass are converted into pure energy, according to Einstein's famous equation. Energy is equal to mass, multiplied by the square of the speed of light, is 4 million tons per second. This is the mass of a large oil tanker. Every second, it is converted into light and heat. The total solar radiation power is approximately 385 septillion watts, 3.85 x 10 to the 26th power watts. This is more than all the energy consumption of humanity for 1 million years. It is released every second. And the sun is an ordinary, insignificant, a remarkable star. Blue supergiants, the brightest main sequence stars, can emit in 1,000,000 times more energy than the sun. Every second, they throw into space as much light as the sun produces per year. But even this pales in comparison to what happens during stellar death. A supernova is the explosion of a massive star, and at the end of its life, it releases more energy in a few seconds than the sun will produce over its entire lifetime. Approximately 10 to the power of joules. The number is so huge that it doesn't make intuitive sense. Let's try to imagine it differently. If it were possible, if you were to collect all the energy from a supernova and use it to light a 100-watt light bulb, that light bulb would burn trillion years. A few weeks after the supernova explosion can emit more light than the entire galaxy it's in. One dying star outshines hundreds billions of living stars. The supernova of 1054, the one that left the Crab Nebula, was visible to the naked eye during the day for 23 days. It was visible at night for almost 2 more years, and it was at a distance 6,500 light-years. Supernova 1604. The last supernova observed in the Milky Way was visible without a telescope for a year. Johann Kepler studied it and left detailed notes. More than 400 years have passed since then, and we are waiting for the next supernova in our galaxy. Statistically, it should have happened a long time ago. On average, supernovae in the Milky Way happen once in 50-100 years. Either we're unlucky, or the last supernovae were hidden from us. Field clouds in the galactic disk. But supernovae are only the beginning of the catalog cosmic violence. There are even more destructive events. Gamma-ray bursts, short bursts of gamma radiation, the most energetic form of electromagnetic radiation. They last from fractions of a second to several minutes, and during this time, they release more energy than the sun produces in 10 billion years. A typical gamma-ray burst emits about 10 in the 47th degrees of joule, 1,000 times greater than a typical supernova. Sources: gamma-ray bursts are catastrophic events. The collapse of the cores of supermassive stars into black holes, the merger of neutron stars. The energy is emitted in the form of narrow beams, jets, which makes the flare even more intense for an observer located in the path of this beam. If a gamma-ray burst occurred in our galaxy and its jet was directed at Earth, the consequences would have been catastrophic. At a distance of up to several thousand light-years, it could destroy the ozone layer, exposing the surface planets to the deadly ultraviolet radiation of the sun. Some researchers link the Ordovician-Silurian mass extinction, the second largest in Earth's history, occurred around 450 million years ago, with a possible gamma-ray burst in relative proximity to the solar systems. This is a hypothesis, an unproven theory, but it shows how life is vulnerable to cosmic violence, and gamma-ray bursts occur constantly. Space telescopes register about 1 burst per day. Fortunately, almost all of them occur in distant galaxies, distances of billions of light-years. The danger to Earth is statistically small, but it's not zero. Let's go up another notch on the energy scale. Quasars. A quasar is an active nucleus, a galaxy in which a supermassive black hole is devouring surrounding matter at an incredible rate. Matter, falling into a black hole, it heats up to billions of degrees. Before it disappears beyond the event horizon, emits a colossal amount of energy. A typical quasar shines hundreds of times brighter than the entire galaxy in which it resides is located. The brightest quasars emit 1 trillion times more energy than the sun. But this luminosity is constant. Quasars can burn for millions of years until they exhaust their available matter. The total energy released during their lifetime quasar surpasses anything but the most extreme events. And these extreme events are the merger of black holes. On September 14, 2015, LIGO detectors first registered gravitational waves, ripples in space-time predicted by Einstein 100 years ago. The source was the merger of two black holes at a distance of approximately 1.3 billion light-years from Earth. Each black hole had a mass of about 30 solar masses. They circled around each other, gradually drawing closer, until they merged into one black Dora with a mass of about 62 solar masses. Wait, 30 plus 30 equals 60. Where did the other three solar masses go? They turned into gravitational waves. Three solar masses, approximately 6 million trillions of kilograms, were completely converted into spatial distortion energy in a split second. This is approximately 5x10 to the power of joules in less than a second. The power at this moment exceeded the combined luminous power of all the stars in the observable universe. All stars in all the galaxies combined. And that was just the first registered merger. Since then, the League and its European counterpart Virgo have discovered dozens of similar events. They occur constantly throughout the universe, continually shaking the fabric of space-time. But there are mergers even more grandiose. In April 2019, an image of the shadow was published supermassive black hole at the center of the galaxy M87. This black hole has the mass of 6.5 billion suns. Imagine the merger of two such monsters. Similar. The events likely occurred in the past when galaxies collided and their central black holes merged. The energy of such mergers exceeds everything we've discussed so far by many orders of magnitude. But even that's not the limit. There is a hypothetical limit, a maximum energy that can be concentrated at one point. This is related to the so-called Planck energy, the scale at which quantum effects and gravity become equally important. The Planck energy is about 2 gigajoules. This is not much by human standards, roughly the energy of a full tank of gas. But the whole point is concentration. This energy must be concentrated in a volume of Planck length 10 to the power of 35 meters. If we achieve such a concentration, our understanding of physics is completely destroyed. Space and time lose their usual meaning. Perhaps a tiny black hole appears. Perhaps something even stranger is happening. And this is where we come to the most mysterious event in the history of the universe, to the moment when all the energy of the cosmos was concentrated in an unimaginably small volume, to the Big Bang. But more on that in the next part of our journey. Now let's stop for a moment and look back. We have traveled all the way from the Earth, a small stone ball nestled near an ordinary yellow star, to the Border's observable universe. We saw stars capable of swallowing the orbit of Saturn, galaxies containing trillion suns, structures stretching for billions of light years. We saw energies that make the concept of many meaningless: supernovas, gamma ray bursts, black hole mergers, events so powerful that the language breaks down when trying to describe them. And we saw that all this is only 5% of what exists. The rest is hidden in the shadows, invisible and misunderstood. The universe. It turned out to be not just big, it turned out to be unimaginably, indecently, offensively huge. So much so huge that the very concept of size loses its meaning, and at the same time, almost empty. Remember the oranges at the beginning of our conversation? One in Moscow, the other in Novosibirsk. It was about the stars and galaxy. But the galaxies themselves, like those oranges, are in an even emptier space. If galaxies were oranges, the closest ones would be several meters apart. This is not so dramatic, but the distances between galaxy clusters are measured in hundreds of millions of light years. The emptiness there is so absolute that even a single hydrogen atom is rare. Voids, giant voids between the filaments of a large-scale structure, can extend for hundreds of millions of light years and contain practically nothing. A lot of galaxies, practically zero galaxies. Areas space where matter is almost completely absent. If you were to teleport to the center of a typical, you wouldn't see anything. Nothing at all. The sky would be completely black, in all directions. The nearest galaxies would be so far away that even the most powerful telescope would barely be able to discern them. You would be alone in a void of such scale that light would take hundreds of millions of years to reach the nearest point with any matter. And this emptiness is not an exception. It is the norm. This is what most of it consists of. The universe, matter with all its stars, planets, galaxies. These are rare. The islands in the ocean are nothing. We, humans, exist on one of these islands. We look at the sky and see stars. We think that space is full of light and matter. But this is an illusion of the observer. We are where there is something. Emptiness does not produce observers, so we do not see emptiness. We see only those rare places where there is something. And now you can begin to feel the scale of space. Not through numbers are too abstract. Not through comparison, comparisons are too limited. Through silence, through the realization that there's a chasm between the stars and an even bigger chasm between the galaxies. Between clusters, an immeasurable abyss. And everywhere, at every point of this abyss, there is absolute silence, because sound does not, it spreads in a vacuum, because there's no one to hear, because there's nothing to hear. Here, the cosmos is silent. It was silent before the first stars appeared, and it will be silent after the last stars will go out. And only here, on this tiny stone ball, circling around an unremarkable star on the outskirts of an ordinary galaxy, only here someone listens and tries to understand. Everything. What we have discussed so far is the scale of space, the hierarchy of cosmic structures, the energies of stellar catastrophes, was only a preparation, a foundation for the main question. What does all this mean for us? Not for science, not for astronomy, not for the abstract knowledge, for you personally, for humanity, for every living thing that has ever existed on this planet. Let's start with the most frightening aspect, cosmic reality, from the fact that most people prefer not to acknowledge. The universe is mortally dangerous. We live on a thin film of solidified lava surrounding a ball of molten iron. This film floats on a mantle of semi-liquid rock, which periodically erupts in the form of volcanoes and earthquakes. We have a very thin layer of atmosphere that protects us from cosmic radiation and meteorites. This layer is so thin compared to the size of the planet that if the Earth were an apple, the atmosphere would be thinner than its peel. And this fragile system is in space, where literally everything is trying to destroy it. Let's start with the immediate threats. Space asteroids boulders left over from the formation of the solar system. They continue to wander in orbits that cross the path Earth. 66 million years ago, one such object, about 10 kilometers in diameter, crashed into the Yucatan Peninsula and destroyed 3/4 of all species on the planet, including non-avian ones, dinosaurs. This was not a unique case. It was another episode in a long history of space bombardments. Rediford Crater in South Africa, about 300 kilometers in diameter, remained from an impact 2 billion years ago. The Sudbury Crater in Canada, 130 kilometers, formed 850 million years ago. The Earth bears the scars of hundreds of major impacts. Most of them are hidden by erosion and plate tectonics, but they were and will be again. Astronomers track thousands of near-Earth objects. Most of them are safe. Their orbits do not intersect with ours or intersect at points where Earth would be in another time. But not all objects have been discovered. Small asteroids with a diameter of tens of meters can appear out of the darkness without warning. Chelyabinsk. The 2013 meteorite was only about 20 meters in diameter. It exploded in the atmosphere at an altitude of 30 kilometers. The shockwave blew out the windows of thousands of buildings. And it was an object the size of a house. The Tunguska event of 1908. Probably the explosion of a larger object with a diameter of 50 to 100 meters knocked down trees area of more than 2,000 kilometers. If it had exploded over the city, the consequences would be catastrophic, but asteroids are only the most obvious threat. The sun, the home star, the source of life and warmth, is also a potential killer. Solar flares throw billions of tons of charged particles into space. When these particles reach Earth, they interact with the magnetic field and the atmosphere. This is usually harmless. We see the aurora borealis, but powerful flares capable of causing geomagnetic storms that can disrupt power grids and satellites. The Carrington event of 1859. The year was the most powerful geomagnetic storm on record and caused disruptions to telegraph systems around the world. Operators received electric shocks. Telegraphs worked even after being disconnected from power sources, powered induced currents. If a similar event occurred today, the consequences would be incomparably more serious. Modern civilization depends on electricity and electronics. High-voltage power line transformers could fail en masse. Replacing them would take months or years. Communication and navigation satellites would be damaged or destroyed. Estimates of the economic damage from a Carrington-level event today are measured trillions of dollars. The social consequences are unpredictable, and such events are inevitable. The question is not whether the next superflare will happen, and when exactly. Well, let's see. Further away is the sun. The nearest stars seem safely distant. 4 light years. This is the distance light travels in 4 years. What could threaten us from such a distance? It turns out, a lot. If a sufficiently close star were to explode as a supernova, the consequences would be significant. Even at distances of tens of light years, gamma rays and cosmic rays would reach the Earth, damaging the ozone layer and exposing the surface to deadly radiation. Less than 30 light years away, a supernova could cause a mass extinction at a distance of less than 10 light years, sterilize the planet's surface. Fortunately, there are no stars in the immediate vicinity of the sun that are ready to explode in the near future. The closest serious candidate is the white dwarf Ike Pegasus. At a distance of 150 light years, could potentially become a Type Ia supernova, but not in the next millions of years. Betelgeuse, which we mentioned earlier, is located at a distance of about 700 light years, far enough away that its explosion will not cause any damage to the Earth. We will see a magnificent celestial spectacle, but not moreover, the stars move. The sun revolves around the galactic center, making a complete revolution, for about 230 million years. During this time, it passes through various areas. The Milky Way, encountering different stellar populations. Sometimes it passes through the spiral arms, the denser region stars, and more active in terms of star formation and stellar death. During such periods, the probability of a nearby supernova increases. Some researchers suggest a connection between the passage of the sun through the spiral arms and the periodicity of mass extinctions on Earth. This is speculative, a hypothesis that has not been definitively confirmed, but it shows that our destiny is linked to the movement in the galaxy. And now let's look into the future, the distant future. In 4 to 5 billion years, the galaxy Andromeda will collide with the Milky Way. We've already mentioned this event. But we haven't discussed its consequences. When galaxies collide, but the stars in them almost never collide with each other. The distances between stars too big. It's like a collision of two swarms of bees. Individual bees fly past each other, but the gravitational effects will be colossal. The orbits of the stars will be distorted. Some stars will thrown out of the galaxy entirely into intergalactic space. Others will be captured for new, unpredictable orbits. The solar system could end up anywhere, closer to the center of the United Galaxy, further away from it, or even thrown into the void between galaxies. However, by that time, it will not matter for the Earth, because in about 1 billion years, long before the collision of the galaxies, the sun will become bright enough to vaporize the oceans. In 5 billion years, it will become a red giant and possibly engulf Earth. Our planet is doomed. It's only a question of timing and circumstances. But even if humanity or its descendants leave Earth and spread throughout the galaxy, it won't save him from the final fate of the universe, because the universe has a future, and that future is dark. Remember what we discussed earlier. The universe is expanding, and this expansion is accelerating due to dark energy. Galaxies are scattering faster and faster. Everything outside our local cluster will eventually be carried away. The cosmological horizon and will become forever out of reach. In trillions of years, if the laws of physics do not change, intelligent beings in the Milky Way will see an empty sky. No other galaxies, no cosmic microwave background radiation, nothing. They won't be able to know that the universe was once young and full of light. But that's just the beginning of a long decline. Stars don't last forever. They burn hydrogen, turning it into helium. When the hydrogen runs out, the star dies, explodes, or sheds its outer layers, leaving behind compact remnant. The most massive stars live only a few million years. Stars like the Sun are about 10 billion years. The smallest red dwarfs can burn for trillions of years, but even they will eventually go out. In 100 trillion years, about 10,000 times longer than the current age of the universe, the last stars will burn out. Galaxies will become graveyards. White dwarfs, neutron stars, black holes, dark planets without suns. This will be an era of degeneration. The term is cold and technical, but it accurately describes the state of the cosmos. No new light, no new heat, only slow cooling and decay. White dwarfs, the remnants of intermediate mass stars, will cool for quadrillions of years until they become black dwarfs, cold, dark balls of degenerate matter. Not a single black dwarf has yet formed. The universe is too young. For this purpose, neutron stars will also cool, albeit more slowly. This is due to superconductivity in their cores. Planets deprived of starlight will become icy worlds with temperatures just a few degrees above absolute zero, and so they will pass eons. But even this is not the end. There is a hypothesis that protons, one of the basic building blocks of matter, are unstable on very long time scales. Theories. The Grand Unified Theory predicts that the proton should decay extremely rarely, but inevitably. If this is true, then in 10 to the 34th to 36th power of years, the number 34 zeros, all protons in the universe will decay. White dwarfs, neutron stars, planets. Everything consisting of ordinary matter will dissolve into the sea. Radiation and elementary particles, only black holes will remain. And here comes the final act. Stephen Hawking showed that black holes don't last forever. They slowly evaporate, emitting what's known as Hawking radiation, a quantum effect that is extremely weak for massive black holes. A massive black hole several solar masses will evaporate in 10 years. Supermassive black holes in 10 years degrees of years. 10 to the power of 10. 1 with 100 zeros. This number is so great that all the time scales we have discussed so far are lost in it without a trace. Age universe. 13 billion years is a 1 followed by 10 zeros. The difference is 90 orders of magnitude, the incomprehensible abyss of time. And when the last black hole evaporates, what will remain? Photons scattering in infinity at the speed of light, more and more rare. Electron particles and positrons remaining from the annihilation of matter, separated by distances greater than the current observable universe. And space, infinite, cold, a dark space devoid of any structure, any processes, any events. This is called heat death. The universe, a state of maximum entropy from which no escape is possible. Nothing can happen because there is no energy gradients, no differences, no change, absolute eternal silence. This is the most likely scenario for the future based on our current understanding of physics. There are alternatives. A big rip if dark energy gets stronger and tears apart even atoms. A big crunch. If dark, the energy will weaken and gravity will take over. Cyclical models, where the universe is reborn in a new Big Bang. But the standard prognosis is heat death, a slow, inexorable decline. And now we can ask the question that really matters. What does it all mean? We've discovered that the universe is unimaginably huge. So vast that the human mind breaks down when trying to comprehend it. We discovered that it is almost completely empty. Matter, a rare exception in an ocean of vacuum. We discovered that it is deadly. Asteroids, supernova, gamma-ray bursts, catastrophes lurk at every turn. We discovered that it is doomed. In unimaginable ions of time, all light will go out, all structures will disintegrate, and only a cold emptiness will remain. At first glance, this is a depressing picture. We are tiny, fragile, ephemeral creatures lost in an indifferent cosmos. Our planet is a speck of dust. Our galaxy is a drop in the ocean. Our life is a moment. But there is another way. Look at this. This whole unimaginable universe with its galaxies, stars, black holes, don't know about themselves. It exists, but it's not aware of its existence. Stars don't understand that they shine. Galaxies don't understand that they rotate. Black holes don't realize they're devouring matter. Only here on this tiny planet, and perhaps elsewhere, in other worlds, matter awakened. It became aware of itself and began to ask questions. We are the universe's way of knowing itself. This is not a metaphor. It is literal. Truth. The atoms you are made of were created in the cores of dying stars billions of years ago. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of this was thrown into space by supernovae before gathering into the cloud of gas that formed the solar system. You literally made of stardust. And this stardust somehow gained the ability to look at the sky and be surprised. It's a miracle. The only real miracle we know for sure. And here comes a strange paradox. We know that the universe exists. We know its size, its age, its structure. We can predict its future trillions of years into the future. But we still don't know if we're alone. The Fermi paradox, one of the greatest mysteries of modern science. If the universe is so large and old, if there are hundreds of billions of galaxies with trillions of planets, why don't we see traces of other civilizations? Where everything? There are many possible answers. Perhaps life is an extremely rare phenomenon. Perhaps the transition from simple chemistry to self-replicating molecules is so unlikely that it occurs only once per galaxy, or less frequently. Intelligent life may be rare. There may be plenty of planets with bacteria and algae, but very few planets where evolution has produced thinking beings. Perhaps technological civilizations are short-lived. Maybe they destroy themselves with nuclear wars, environmental disasters, artificial intelligence, before manage to spread throughout the galaxy. Perhaps space really is dangerous, and civilizations are regularly destroyed. Gamma-ray bursts, supernovae, asteroids, maybe interstellar travel. Impossible in practice, and each civilization is locked on its home planet or in its own star system. Perhaps advanced civilizations exist, but we cannot detect them because their technology is not distinguishable from natural phenomena for our primitive understanding. Perhaps they are deliberately hidden. Perhaps. The galaxy is full of danger, and it's wise not to draw attention to ourselves. We don't know. After decades of searching, network programs listening to the sky on radio waves, hunting for exoplanets, searching for biosignatures in the atmospheres of distant worlds, we found nothing, not a single one, compelling evidence for the existence of other intelligences. This does not mean that we are alone. The absence. Evidence is not evidence of absence. Space is vast, and we've only just begun to search. But the silence is deafening, and here all the threads of our journey converge. We started from the surface of the Earth and went up to the boundaries of the observable universe. We saw the scale space and time that defy human perception. We are confronted with energies that are destructive stars and shaking the fabric of reality. We looked into the future, where all the lights will go out. And at the end of this journey, we found themselves tiny, fragile, ephemeral, but also unique witnesses known to us. The only ones who look at the stars and Micaiahs asked and asks, why does the universe doesn't have meaning in itself? Meaning is something we bring to the table. Meaning arises when matter becomes complex enough to ask questions. And maybe, just maybe, that's where our cosmic role, not to conquer and subjugate, not to spread and multiply, but to be a witness, to watch the sunset and understand that this is the same star that was born from gas clouds 4.5 billion years ago. Look at the night sky and realize that every dot light is the sun, perhaps surrounded by worlds, looking at photographs of distant galaxies and understand that we are seeing the past, light that has traveled billions of years to reach our eyes. It's a privilege, a strange, unexpected privilege out of all the matter in the universe, of the quintillion tons of hydrogen, helium, carbon, iron. Only a tiny fraction formed into structures capable of being aware of its own existence. And you are part of this tiny share. You are a rarity, on a cosmic scale, not because you're special, but because consciousness itself, a rarity of cosmic proportions. When you look at the stars, the universe looks at yourself through your eyes. When you ask questions, the universe asks questions about yourself. When you feel awe of infinity, the universe feels awe of yourself through you. This is not mysticism. This is physics. You are part of the universe, and yours consciousness is part of what the universe does. And now, at the end of when you travel, you can look at the night sky in a new way, not as a ceiling with lights, not as a beautiful a picture, but as if into an abyss, the abyss of space, where distances are measured years of light travel, the abyss of time, where events took place billions of years ago and will continue to happen trillions of years from now, an abyss of possibilities, where worlds exist that we will never know about. And at the center of this abyss, the point of consciousness, the observer, the witness you are. We don't know if there is other observers. We don't know if intelligence will survive long enough to witness the eras of degeneracy and evaporation of black holes. We don't know if anyone will ever find a way to survive the heat death of the universe. We don't know why all this is, but we know that it exists, that it's real, that it is beautiful and terrible at the same time, and we know we're here to see it. Maybe that's enough. Space is silent. It was silent before us and will remain silent after us. But while we are here, there is someone to listen. There is someone to be surprised. There is someone. Remember, let this silence not be frightening, but peaceful. Let infinity be not oppressive, but liberating. Let the awareness of one's own smallness will bring not despair, but peace. Because we are not simple, not just specks of dust in space. We are specks of dust who know they are specks of dust, and that changes everything. Thank you for taking this journey with me. Thank you for looking at the stars. Thank you for asking questions. Now close your eyes. Imagine the Earth floating in the void. Imagine the solar system lost in the arm of the galaxy. Imagine a galaxy drifting in a cluster. Imagine clusters connected by filaments into a cosmic web. Imagine the observable universe surrounded by an infinity of the unknown. And somewhere in the center of it all, this is why you breathe, listen, exist. This is enough. Good night, M.